Hey guys, welcome back to this mini-series on neural networks and what they entail. Last week we talked about backpropagation in minuscule, but now I would like to talk about backpropagation in a more in-depth review. Hey guys, my name is Cesar Hernandez, and I'll be talking about backpropagation. So backpropagation is an optimization algorithm, as we knew, and is used in training neural networks. It calculates gradient to update weights and minimize the cost function. It works with gradient descent to improve learning efficiency. How is it helpful? We'll see that in the future. What is backpropagation? Backpropagation, as we know it, is an algorithm used in training neural networks to adjust the weights and minimize error. It works by propagating the error from the output layer backwards through the network using the chain rule of calculus, allowing the model to update its weights efficiently. This process, combined with gradient descent, helps the network learn from data and improve accuracy over time. An analogy for backpropagation is like a student learning from mistakes on a math test and going back and reviewing the test itself. Calculating the error. The error loss quantifies the difference between the network's output and the actual target. Common loss functions include mean squared error, MSE, and cross entropy loss. Thus, error is the basis for updating the network's weights. So we'll use the error to adjust and fine-tune the weights going forward. The forward pass, it allows for input data passes through the network layer by layer. Each neuron processes the inputs, applies the weight, sums them, and passes through an activation function. It produces an output that is compared to the target error. The backward pass, or backpropagation, is an efficient computation of gradients. It is achieved through an algorithm called backpropagation. The algorithm calculates gradient of the cost function with respect to each weight and bias, and allows the network to learn from each training example. Errors are propagated backwards from the output layer to the input layer. The algorithm calculates the gradient of the loss function with respect to each weight, and it utilizes the chain rule from calculus to compute these gradients efficiently. The weight update. So weights are adjusted in the direction that reduces the error. The learning rate determines the size of these adjustments, and this process is repeated over and over as many times to reach minimal loss. The mathematical foundation. Backpropagation applies the chain rule to compute partial derivatives. It helps determine how much each weight contributes to the error. The error loss quantifies the difference between the network's output and the actual target. The common loss function includes mean squared error and cross entropy loss. The error is the basis for updating the network's weights. The challenges seen in backpropagation is vanishing and exploding gradient can impede learning. Proper initialization and activation function choices can mitigate these issues. Regularization techniques help prevent overfitting, but here are some solutions. We could use a redo activation, which prevents vanishing gradients, batch normalization, which stabilizes learning, and adaptive optimizers such as Atom, RMS prop, which adjusts the learning rates dynamically. The learning outcome is that backpropagation is a crucial algorithm in training neural networks, enabling them to adjust weights and improve accuracy through minimization. It works by propagating errors backwards and using gradient descent for optimization. Understanding backpropagation helps in designing more efficient and effective models. Despite challenges like vanishing gradient optimization such as redo batch normalization and adaptive learning rates enhance its performance. As deep learning evolves, continuous improvements in backpropagation and related techniques will drive advancements in artificial intelligence. Thank you for joining me in this chapter, and I'll see you guys in the next one.